So solution 1 is in equilibrium. There's no stoichiometry involved. So this is just an ice table. Remember, we diluted because we mixed 61 point, in this case, 61.31 milliliters of 0.3 molar, 38.76 milliliters of 0.3 molar. So I do my M1 V1 divided by M2 V2, and I get my new initial concentrations. Okay, so my initial for acetic acid is 0.1838. This is 0. Initial is 0.1162. 0 molarities. Change is x, right? Plus x, minus x. Equilibrium is 0.1838 minus x. 0.1162 plus x. However, we're assuming that x is fairly small, and since we could use the quadratic, so k is equal to h plus ac minus HAC. It's equal to, for acetic, 1.76 times 10 to the negative 5. And this would be x squared divided by 0.1838 minus x. Oh, wait, no, it's not x squared. It's 1838. You're telling me it's the same question. And we can solve for this. So I'm just going to take 0.176 times 10 to the negative 5, multiply it by 0.1838, divide it by 0.1162. So I can do that, or I could have used the Henderson-Hasselbalch. pH equals pKa plus log base acid. Here. I'm going to show you. I'm just videoing it because I know that there's going to be 30 other people with the same questions. In fact, I'm kind of surprised nobody has called me yet.
So far, I think I'm good.
Alright, so this will get me the same answer. pKa for, I take the negative log of 1.76 times 10 to the negative 5. I think it was 4.75. I'm pretty sure it's 4.75. In this case, our base is 0.1162. The acid is 0.1838. And we get that answer. Done. By the way, it's kind of a trick question. What is the predicted pH of this? How do we start off this lab?
By predicting.
By figuring out what volumes we needed to make a pH of, what did we say, 4.55. So it better be 4.55, but hopefully this is 4.55. Alright, so that's how I figure out the pH of a buffer. I still need to know how to do it in case wasn't given it from the beginning. So you did your hard end on calculating these volumes. Now that I know the volumes, I can calculate, or if the volumes ended up being different from what you thought they were going to be, we can solve it this way. Problem 2 is stoichiometric. The HCl is going to completely react with, it's an acid, so it's going to completely react with the base. So which one is it going to completely react with? HAC or AC?
AC.
AC. So acetate ion. So it's going to completely react with the acetate ion as the limiting reactant. And then I'll know how much I have left. So I go back to this. I need to figure out the sort of the equilibrium, or at least the new initial values after the stoichiometry. So here I had, oh, it gets a little ugly because I do another slight dilution. I took 20 milliliters of 0.1838 molar, but then I added 1 milliliter, so it's going to be in 21 milliliters. So I don't know what that is. I'll write it down here. H plus, I have 1 milliliter times 0.5 divided by 21 milliliters. And AC minus, I have 20 milliliters times 0.1162 was the initial, divided by 21 milliliters. Okay, so calculating these, let's figure these out real quick. Go ahead and pause it.
Oh, you can pause it. Aha!
All right. So this is my initial molarities. All of the H plus is going to react. All of the HCl is going to react with the acetate. So I'm going to subtract this. So that means I'm going to make more. It's going to be reverse reaction. It's going to react with this, and the reverse reaction produce this. It's not really an ice table, but we get the same effect. We're really doing stoichiometry. It works the same. All right, so this is going to be 0. This is going to be
Yeah, she could do it.
You do this one. 0.1988.
0.0869.
Okay, so these are my now new molarities. This stays the same. This changes. So still 4.75. Again, technically this wouldn't be in equilibrium, now it's 0, but we're really doing stoichiometry. I'm just using the same math concept to get stoichiometry of what are the species. So this is my initial. Now this and this are going to be in equilibrium, reach a new equilibrium. So this is 0.0869, 0.1988 molarity. Okay, so that would be how I calculate that one. This is just stoichiometry. I just need to know how many H plus ions I have. This is all the HCl is going to dissociate. This is an easy one. If all of it dissociates, then I just figure out what is the, I just have to figure out the diluted molarity, because I started with 20 milliliters of water. I added 1 milliliter of 0.5 molar. I just have to figure out what the molarity is of the HCl after it's been diluted by the water, and take the negative log of that, because all of it will be present as H plus ion. And the last one is another. This is just HAC. Okay, this, I'm not able to use Henderson-Hasselbalch. I got to do it the long way, because I don't have enough of the other ones present, or at least by the time I do, I'm just better off calculating it. All right, the initial concentration, this is pure acetic acid. So what is the initial concentration?
0.3.
0.3. 0, 0. Minus x plus x plus x. And this would be 0.3 minus x. This would be x. This would be x. I know K is equal to 1.76 times 10 to the negative 5 is equal to x times x divided by 0.3 minus x. Oh, I got a quadratic coming, don't I? Or do I? How do I know whether I have to do a quadratic or not? Which one is the problem maker? Why is this becoming a hard math problem?
That x squared is probably me.
No, the x squared is not a problem. I can deal with x squared. This one is the one that makes it ugly, right?
Yes.
If I could get rid of this x, then this would be just like quick algebra. But if with that x, now I have to, like, you know, distribute it through, and I end up with a polynomial, and that's where. So if I could get rid of this x, so my whole approximation is, if this is like 0.0001, well, then it's still pretty much 0.3. So if x is much, much, much smaller than 0.3, I could just say, well, I'm just going to ignore that. It'll be a little factor, but it's, you know, kind of like back here. If I used 100 milliliters instead of 100.06, it does change things a little bit, but probably small enough it's not going to matter. So if x is small, and the rule is 5%, if x is less than 5% of this, so 3 times 5 would be 1.5, 0.015. So it'd be like, has to be less than 0.015, if I did the math right in my head. Then I'm okay. The answer is, I assume x is small, I calculate it, and then I see what is x, and is x too, I just can ratio it. So, all right, x, I'm going to assume that this is small, which means this is just x squared is 0.3 times 1.76 times 10 to the negative 5, right? Which is what?
Negative 5.28 times 10 to the negative 5th.
We did something wrong. Shouldn't be negative. Did you do a negative somewhere in there?
I sure did. I put a negative 3 instead of
Then I'll ignore
0.3.
it. Okay, so what was it? What was the number?
5.28 times 10 to the negative 5th.
And that's x squared, so now I want to take the square root of that.
Point 0023.
So by the way, x is representing H plus, so this is my H plus concentration, so I can take the negative log of that to get pH. But let's go back and check if this was fair. Take 0.0023 and divide it by 0.3.
Point 0077.
In percent, that's 0.77%, right? 1, 2. This is well below 5, so I was justified. I'm safe. If this turns out to be 9 or 12, then I have to go back and redo it and use a quadratic. It's like, well, that's going to be substantially different, enough to affect the final answer, so I need to go back. This is much smaller, so I can always double check and justify. So then I take the negative log of this, because this is representing H plus concentration in equilibrium, and I get the pH. And that's how we do all of them.